which when plotted the result in a curve always upwards or not curving at all is called a convex function. Is called a convex function. So we represent the single variable convex function which is defined as let x and y be 2 points. This is x-axis and this is y of x, and the position of the curve is upwards. This is known as the convex function. Here the function f is defined as lambda x plus 1 minus lambda into y. And this shows that lambda into fx plus 1 minus lambda into fy represent this convex function. So any function which when we plot it and the result of the curve is upwards is known as the convex function, and downwards is known as the concave function. So this is we write as a theoretically, but for differential calculus when we use the differential calculus how to check the function is concave, convex, or neither concave nor convex. So by using differential calculus we have some definition. That means we write as function of single variable fx. You noted this, Bhavna, Dipanshi, Manshi, Nakshi? Okay. Okay. Dear all, you have noted this, and related to this, questions will be asked in the exam. Mathematical questions, numerical questions, same. So we use calculus, a function of single variable. Let we write as fx be a function of single variable fx be a function of single variable Then the second derivative, the second derivative d square f upon dx square, because we have only a single variable, which is less than or equal to 0 for all values of x. So then the function has local or relative maximum, local or relative maximum, to be also the global maximum. We can say that to be also the global maximum. We draw the figure you have seen in previous lecture: local minimum, local maximum, global minimum, global maximum. And when we change the sign, that means the sign less than equal to sign, if we write as in second part d square f upon dx square, which is greater than equal to 0 for all values of x. So the function has local, or we can say that relative minimum, local or relative minimum, to be also a global minimum, to be also a global minimum. If d square f upon dx square equal to 0, so neither convex nor concave, so we need to the further investigation. Here we also check the concavity and convexity. So this function we write as, when we check such type of things, and if d square f upon dx square is less than equal to 0, so this function is known as the concave function. Here you note this is concave function. This is concave function, and for this case, this represents the convex function. Convex function. So you have to remember that questions can be asked on the basis of convex and concave. Any function is given, so question can be asked: the given function is convex or concave. So you have to solve the questions. That means function f(x) is given. This is for single variable. Then next problem we take for the two variable. Two variable means we involve y as a variable, independent variable also. So we start with problems. First we solve the concave, convex, then we move for the Hessian matrix and other part of the NLPP. Noted? Okay. d square f upon dx square is equal to 0, so we can write directly neither concave convex. That means we need to the further investigation. Done. We have okay. Okay. Now we take one problems related to convex or concave. We start with a simple problem. That means if fx is equal to tan minus x square. If fx equal to tan minus x square, check this function. That means we write as this function check this function is concave, convex, or neither. So we have to check the concavity and convexity. So just we write the function fx. We write as fx equal to tan minus x square. This is the equation number 1. We calculate the first derivative. That means df upon dx for stationary value. So when we obtain first derivative, that means tan is the constant, differentiation is 0, 0 minus 2x. So 0 minus 2x, and second we check the value of d square f upon dx square. So d square f upon dx square gives us minus 2, which is constant. Here we put df upon dx equal to 0, so then you can obtain the value of x. So that means we can write as minus 2x equal to 0, which gives us x equal to 0. So here x equal to 0. But when we obtain the second derivative, so gives us d square f upon dx square, which is minus 2. That means negative. So minus 2, with this value is less than or equal to 0. That means less than 0 always. So we cannot write equal to, we write only less than. So we write as this value less than 0 always, because this is constant value, always less than 0. So in such case, we write as always for all values of x. We also mention this for all values of x, for all values of x. So hence the function fx is concave, is concave. So just to show that the given function which is convex, concave, or neither. So we have to remember that means d square f upon dx square, which is less than or equal to 0, which is concave for all values of x. So here when we obtain the second derivative gives us constant value. That means there is no chance to put any value of x. That means we change this value, always remains same. So we write this less than 0 always for all values of x. For second problem, try to solve this problem and tell me what is about the concavity or convexity of this function. If fx equal to x raised to the power 4 plus 6x square plus 12x is concave, convex, note this problem and try to solve. or neither. Fx equal to x raised to the power 4 plus 6x square plus 12x is concave, convex, or neither. You have 2 minutes to solve this problem. Done? No need to calculate the value of x. Just you obtain the second derivative. On the basis of second derivative, you can tell about the function is concave or convex. But we need the value of x also, and we have to check the value of x are positive or negative. Done? Okay. Convex for concave? Right in chat box. Yeah, convex. Good. Good, good. So just we obtain the first derivative. That means we have the function fx equal to x raised to the power 4 plus 6x square plus 12x. So just we obtain first derivative df over dx. So we write as 4x cube plus 12x plus 12. Similarly, we obtain the second derivative. So we see that the second derivative is 12x square plus 12. So you can put df on dx equal to 0, calculate the value of x here. But we see that the second derivative. When we see the second derivative, d square f upon dx square. So we have the term x square. We have the term x square. So according to x square, when we obtain the value of x here, some value of x are positive. Suppose x gives the three values. So that means two values are positive, one value of x are negative. Suppose. So when we put here the negative value of x, that means square of the negative value also give the positive value. Understand? And square of the positive value also give the positive value. So just we see the second derivative. So for any value of x, we write as for any value of x. That means x may be positive or may be negative. So the d square f upon dx square here always positive. here always positive. So that means we write as d square f upon dx square is always positive. That means greater than equal to 0. So greater than equal to 0, ये convex function. Convex function. Okay. Now we move for second derivative. Sorry, we move for the two variable functions. That means this is single variable function, but now we talk about the two variable functions. So we have some rule to check the concavity or convexity of two variable functions. But the procedure are same. When we have two variables, then we define derivative of with respect to x or with respect to y. Now we talk about the two variables. That means for two variable functions. That means f of x, y. Function have two variables. So here we calculate del f upon del x and del f upon del y. Del f upon del x and del f upon del y. We put the value of del f upon del x and del f upon del y equal to 0. Find stationary point. Find stationary point. Then we obtain the d square f upon del square f upon del x square, del square f upon del y square, and del square f upon del x del y. So we have to find these values. For condition of concavity or convexity, we construct a table. So we mention in the table where the function is concave, where the function is convex, or strictly convex or concave. Okay, noted. So we construct a table. Dipanshi, Manshi. Okay. So we have a quantity, that means value of the second derivative. We first column mention as quantity. Second, convex. Function is convex or no? Strictly convex. We add some concave and strictly concave. Strictly concave. So first we have to check del square f upon del x square into del square f upon del y square minus del square f upon del x del y to the whole square. We have to check this value. You read in calculus rt minus s square. So rt minus s square. So del square f upon del x square denoted as r, del square f upon del y square denoted as t. and S denoted as del square f upon del x del y. And we write separately del square f upon del x square and del square f upon del y square. So this is our first column. We calculate all the values, and if this value is greater than equal to 0, that means rt minus s square greater than equal to 0. And this also greater than equal to 0. This also greater than equal to 0. Function is convex. For strictly convex, that means we have greater than 0. And if function is greater than 0, so then we say that the strictly convex. Here greater than 0, greater than 0. For concavity, the function this should be greater than equal to 0, and the del square f upon del x square less than 0, and del square f upon del y square less than 0. So this is said to be the concave. And strictly concave, that means greater than 0. This is less than 0 and less than 0. So quantity, that means rt minus s square, and we check r and t, all are greater than equal to 0. We say that the convex, or for strictly convex, we have all value greater than 0 only. So you have to remember this, where the function is concave and convex, and strictly concave and strictly convex. So we start with problem. That means the function fx, capital Fx, which is given as x1 x2 x1 x2 minus x1 square minus x2 square. We use two variables here, represent as x and y, but in questions given as x1 x2, so no confusion. That means we consider as x as x1 and y as y1, x2, sorry, so y as x2. So only variable change, you apply. The function is convex, concave, or neither. For neither, the condition for neither, that means this equal to 0. If this condition equal to 0, so the function neither concave nor convex. You have to understand this. Neither, just we write one column added here. So for neither case, that means this equal to 0. Or if less than 0, so we cannot calculate any concavity or convex. That means our case is doubtful. So the function is concave, convex, or neither. So just we calculate del f upon del x1. Del f upon del x1, here this is x2, x2 minus 2x1, and del f upon del x2, del f upon del x2. So when we obtain del f upon del x2, gives us x1, x1 minus 2x2. And now we obtain second derivative, del square f upon del x1. So this gives us minus 2 del square f upon del x2. This gives us also minus 2. And last we calculate del square f upon del x1 del x2. How to calculate this? We calculate this as del upon del x1 into del f upon del x2, vice versa, because you know that del square f upon del x1 del x2 always equal to del square f upon del x2 del x1. always equal. So when we have del f upon del x2, then we differentiate with respect to x1. So this is del f upon del x2, and when we differentiate this with respect to x1, so this gives us 1. So this gives us 1. So del square f upon del x1 del x2. That means del f upon del x2, we differentiate by with respect to x1, so gives us del square f upon del x1 del x2. So the value is 1. When we put these values in this equation, that means del square f upon del x square, this is minus 2, so you have to write, so this is minus 2, and del square f upon del y square means this is also minus 2, and minus 1 to the whole square. So minus 2 into minus 2, which is 4. 4 minus 1 square is 1, equal to 3. So this gives us 3. 3, which is greater than 0. Which is greater than 0. This is greater than 0. So what this function is shows? This shows that the strictly concave. Because we check all the values also. All the values means del square f upon del x1, del square f upon del x1 square, sorry, you write square 1, and x2 square. So this is also less than 0, and this is also less than 0. So this also less than 0, less than 0. So this function is strictly concave. Strictly concave. Okay. Noted. Ankita, Bhavna, Ankita, Vibha, Vibha Thakur. Okay. So try to solve one question. Fx equal to x1 square plus 3 x1 x2 plus 2x2 square is concave, convex, or neither. Try to solve. Again, you have 2 minutes. out the concavity or convexity, the condition del square f upon del x square into del square f upon del y square minus del square f upon del x del y is greater than equal to 0 in each case. If this value comes less than 0, that means negative. So we write directly no concave, neither concave nor convex. Neither concave nor convex. You have to check this value. So we find del f upon del x1. Del f upon del x1 gives us 2x1, 2x1 plus 3x2, and del f upon del x2 we calculate. So for x2 we write as 3x1 plus 4x2. Del square f upon del x1 square. So we write 2 del square f upon del x2 square. This gives us 4. So you can see both values are constant. This here is 2 and here is 4. So that means this value is always greater than 0. This value always greater than 0. Now we calculate del square f upon del x1 del x2. x1 x2. So you write as del upon del x1 into del f upon del x2. So del f upon del x2. So this is del upon del x1 into del f upon del x2. Del f upon del x2 is 3x1 plus 4x2. So 3x1 plus 4x2. With respect to x1, we write as 3. Del x1, which is 3. So this value is 3. Now we put these value in this equation. We put these value in this equation. That means we write as del square f upon del x1 square into del square f upon del x2 square minus del square f upon del x1 del x2. So here when we put this value, that means 2, 2 into 4 minus 3 to the square. So 2 4 are 8, 8 minus 9. 8 minus 9 gives us minus 1. 8 minus 9 gives us minus 1. So this minus 1, that means which is less than 0. This minus 1 gives us less than 0. So we have to check concavity or convexity of any function. So always this condition, that means RT minus S square, del square f upon del x square into del square f upon del y square minus del square f upon del x del y, always greater than equal to 0. But here this is less than 0. So for in such this case, we write as neither concave or nor convex. So this function we write as this function neither concave nor convex. Neither concave nor convex. Neither concave nor convex. Because this gives us less than 0. 8 minus 9 minus 1, which is less than 0. Okay, Bhavna? Bhavna? Yes. So try to these questions within time limits. This type of questions can be asked. Noted? fx equal to x1 x2, a simple function. Fx we consider as exponent to x2. Check this function is concave or convex. Rt minus s squared less than 0, neither concave nor convex, greater than equal to 0, we have to find convexity or concavity. For strictly convex, greater than 0, and convexity greater than equal to 0. So same, we obtain del f upon del x1 gives us x2, del f upon del x2 gives us x1, and del square f upon del x1 0, del square f upon del x2 square also equal to 0, del square f upon del x1 del x2 del x1 del x2. So we write as del upon del x1 into del f upon del x2. So del upon del x1 into del f upon del x2, this is x1, so gives us 1. So rt minus s square, that means we write as del square f upon del x1 square into del square f upon del x2 square minus del square f upon del x1 del x2. This gives us 0, 0 minus 1 to the square. This means 0 minus 1. This means which is less than 0. The same, neither concave nor convex. Okay.